Yep. So my phone is doing all the audio recording. So which means there might be more noise because it's on the same table that I type and use my stuff. So there'll be a little bit more distraction with the audio track this time. All right. Well, it's better than nothing. The other good news is this computer has no microphone, and that's part of the problem. Is the computer itself has no internal mic, so I can't just say okay, using lesser quality, we'll just go to the internal mic of the computer. It doesn't have an internal mic, doesn't have any camera on it either. So in terms of privacy, it's actually a good thing, but in terms of when on a day like this, not so good. But I'm getting a new computer, so maybe we'll get to use that, either on Wednesday or maybe probably next Monday. We only got, how many classes left? 4 or 5 classes? Yeah. So we are kind of pushing it. And we lost a lot of days, and that's why the second exam is canceled, because otherwise we spend one class to talk about the exam, to take the exam, kind of at least, half of the class to go over the exam questions, and that's like 1.5 classes already. So we're going to cancel the second exam and then just kind of focus on more material. But that means the final exam will also cover more material as well, which is good and bad, because the good thing is it has more topics on it. So everything from CNF is going to be on it. So it has more topics. By comparison, graph stuff is not going to take up the entire final exam like in the past. So it can be a good thing, but there's more to study. So you kind of like toss up there. Yep. I don't want to do it that way. I kind of want the final exam to take up maybe 53% of the final grade, and then the first exam will expand from 20 to 27. So the ratio between the first exam and the final exam will be about 1 to 2. So I want to maintain that ratio. Yep.
Sir, are you planning to grade our homework anytime soon?
Yep.
Yep.
Yep. Well, it'll be graded.
I just want to kind of understand what's a grade.
Ah, okay. Understood. All right, so we're back to the A-star algorithm, and I'm not sure whether I kept the spreadsheet last time of the trace. I'm hoping that I did. So we'll see whether it finds it or not. Did I use LibreOffice? I thought I used LibreOffice last time. Yeah. So recent documents. It may be as old as this. That looks like it. Yep. Okay, that's good. Yeah, it has got a G function, the F function. That's definitely the A-star algorithm. You guys do remember what is the G function versus the F function? I like those answers. Very honest, very candid. It's like, no, I have no idea what you're talking about. All right. So I'm just checking the date. That was 21 days ago, 3 weeks ago. Yep. That was 3 weeks ago. The fire took out quite a few days. And then we lost a Monday because of Veterans Day.
Oh,
So,
yeah, but it wasn't on Monday also.
yeah. So we lost a lot of days. But this class is not nearly as impacted as my cisp440 class, because that's a second 8-week class.
Wow.
Yeah. And this class, there are no other classes that depend on this class, at least at AR. But cisp440 is the beginning.
Yeah.
If I don't have enough time to cover enough material in cisp440, the impact is long lasting. Yep. So this class is not the worst impacted class of all of my classes. And assembly is not as impacted either, because assembly doesn't really lead to other classes. It's not a prerequisite of other classes, at least not here.
You're just not gonna know any information. That's all. They're just not gonna know some information, that's all.
Well, it depends on whether you want to transfer to a computer engineering program or a computer science program. If you're transferring to a computer engineering program, then 310 is still quite useful, at least the way I teach it. All right, so we'll go ahead and resume everything from here. Screen copy, there we go. All of this stuff, it was from the practice exam. So we are backtracking to, yep, that's starting to be part of it. But that's the proof. And this is the picture. Nope. There's a picture of all the H values, the heuristics. That's the one that I want to find. Maybe I was mistaken. I didn't write down any dates, that's the problem. That's definitely the exam stuff. Okay. So let me see. The H values are not here, so I can't really continue without knowing the heuristic values. It has to be somewhere. Did anyone take note of the H values, the heuristic values that I was using for this example?
Maybe you have it on YouTube?
Yep, definitely gonna be on YouTube. I was hoping to find it here, so I can just continue with that slide. If I can't, I can just use YouTube.
I think you use this one.
I think it was for Dijkstra algorithm.
Yeah, I think that's the Dijkstra's algorithm.
But you use the same for A-star.
Yeah, but I need to have the heuristic values. But I can't remember where I wrote down the heuristic values. Yep. All right. Thank you. I'll just write it down and return the notebook. All right. So let me show you what I'm doing here. It's the same picture, but it needs to have the heuristic values. So HBE is 2, HCE is 2.5, H of DE is 1, H of AE is 3. Okay. All right, thank you. There you go. All right. So, I hope you guys still remember what a heuristic value is. So in this case, HBE equals to 2 basically means the underestimate of the underestimate length of the shortest path from vertex B to vertex E is 2. Now you can see it's really a gross underestimate because the actual shortest path is, let's see, 3.6. The length of the actual shortest path is B, A, C, D, E, which has a length of 3.6. So, having 2 is an underestimate, okay? But that's okay. The whole point of the heuristic values is they have to be underestimating. If the heuristic value is not underestimating, then the A-star algorithm is not guaranteed to find the shortest path anymore. Yes?
Is there a specific script that calculates underestimation? Or we just guess the number?
You just pull a number.
But,
In this case, I just pulled a number.
Yeah, but in real world, it's like reasonable, right?
Correct. So, yeah, go ahead.
Well, how we just estimate everything to be 0, do we end up with Dijkstra's algorithm?
Yes. Well, you end up with a search pattern that resembles the search pattern of Dijkstra's algorithm. But it's not exactly the same because Dijkstra's algorithm, or at least the one that I talked about, searches from the destination back to the source. In the A-star algorithm, we start from the beginning to the end. So from that perspective, they're not exactly the same, but you're correct that they both, A-star will degenerate into a breadth first search algorithm. So from that perspective, yes. So they basically will behave about the same. Okay? So getting back to your question, the heuristic function is usually something that's easy to compute and also guaranteed to be an underestimate, and hopefully it is also informative. So having a heuristic function just to map to 0 is super easy to compute. It's guaranteed to be underestimating, but it is useless. Is that okay? But when you're talking about a map, for instance, okay, so let's pull up a map here. So if you're looking at a map, then the over-the-air straight distance becomes a good heuristic because it meets all of those requirements. It is easy to compute, it is underestimating, and also it is informed.
So basically it's like a function that calculates the shortest distance
Between 2 points, correct. Yep. So I guess I don't have to bring up a map after all. Okay. But the idea is the same. It has to be something that meets all the requirements. Underestimating, easy to compute, and somehow it is informing the search
I just tried to tie it back
procedure.
to our example, so because how it came up was 2 or 2.2.
Oh, that's just me
Yeah.
pulling air out of the pulling.
But in
numbers out of
actual
the air.
work, there is a shorter distance.
In the actual application, it depends on what you're doing, because the edges are not necessarily, or the vertices are not necessarily two-dimensional coordinates. They can be states of a processor, for instance, and you're looking for the shortest sequence of instructions to get a certain thing done. So how do you use the shortest sequence of instructions in assembly to get a C statement done? That can be seen as a search, and you end up with a different type of estimate in that case. So in that particular case, the actual cost would be in terms of cycles, right? In terms of the number of actual cycles, but you can underestimate and say, well, we'll assume every instruction takes only 1 cycle. But in reality, some instructions take 2 or 3 cycles. But underestimating every instruction to be only 1 cycle gives you some information, but it's not going to guarantee that, oh, this heuristic is super accurate. But it will give you some information of which way you should go. So is that kind of addressing the question? Okay. Mm-hmm. All right. So getting back to this picture. So the same thing with the h of C to E is 2.5 because from vertex C to vertex E, the actual length of the shortest path is 3. 2.5 is, well, it's an underestimate, okay? So DE, kind of the same thing. The actual edge is 2, but the estimate is only 1. And then from A to E, there are 2 ways to go. The shortest way is 1.1. Ooh, I messed up here, didn't I?
3.1.
Huh? Oh, because of the 2. So it's 3.1, but I chose to use 3 here. So all of these still meet the requirements. Okay? And now we can actually resume because here we can. So there are 3 things we need to look at, which makes it kind of difficult. One is the picture itself. One is the algorithm, and then one is the actual trace. So right now, I believe we are going back to the beginning of the outer loop. So out of the 2 vertices, A and D, okay, let me just take a quick look here. Okay, so the last time we picked out vertex C, and we look at all the outgoing neighbors of C, and when we look at the graph, look at C here, it only has 1 outgoing vertex, D, so we got that done. So that means we are now back to the beginning of the outer loop. So let me show you where we are in the algorithm. So that means we are back to the beginning of the outer loop. We are now evaluating the while loop condition here. So now the question is O as a set empty or not? We know it's not empty, okay? So if you go back here, we see that O has two elements, is not empty. And then the second question is there one vertex in V such that f of V is less than g of x? Now, x is not just any vertex. X is the destination. So it's asking us, do you guys remember what is the difference between the f and the g? Okay, g is based on f. Okay, you were about to answer the question. Go ahead.
Very good question. Isn't G the path, so do you know for certain path is
It's kind of the opposite, but they're close, okay? So f is the actual path, it's the length of the path from the origin to a particular vertex. And then g is the length, is the estimated length of the shortest path from the origin going through whatever the argument is to the destination. So g of x is actually the estimated length of the shortest path, basically. Okay? So this question is really asking, is there anything promising within the vertex, within the set O? Because if f of v is greater than g of x for every single vertex already, then we know that there's no hope. Okay, we cannot hope to find a shorter path anymore. Okay? So now we evaluate whether that is true or not. So maybe it will be helpful to scroll this. I can't scroll this anymore. So I'm going to resize this. The idea is I want the algorithm to be displayed at the top of the screen as much as possible, so I can show the spreadsheet right under that. There we go. Okay. So now we want to evaluate the condition. O is non-empty, okay? So we got the first requirement met. The second requirement is when we look at the f value of all the vertices, are they all less than g of x? Now, which one is x? Which one did we choose as our destination? E is our destination. So g of e is still infinite, which means the second requirement has got to be true. Okay? So when you look at all the f values except for e itself, they are all, less than or equal to infinity. So there's still hope that we can find a shorter path. So now we move on to the next line. The next line is right here. We find a particular vertex in O such that this particular vertex C has the least f value amongst everything in O. Okay, so we look at O, it has two vertices. It has vertex A and vertex B. We look at these two and say, which one is more promising? In other words, which one has the smaller f value? And we look at the f value. Oh, so you're right. Okay, so I got it flipped. G is the length of the shortest path to the vertex, and then f is the estimated length of the shortest path from the origin through a particular vertex to the destination. So I stand corrected. Okay, but we have to find the one that has a smaller value. F of A is 3, and then f of D is also 3. So we can pick either one now. Which one do you guys want to pick? Oh, f of A is 3.5? Oh, okay. So f of D has to be the only one. I didn't see the wrap around of the 0.5 around the second line. So f of D is the only one that we have to pick because it has the least f value. So we continue with the algorithm. We have to pick D as the vertex to expand. And as soon as we pick a particular vertex, we take it out of the set. So now the set O only has A in it. And then we look at all the outgoing vertices of vertex D, and we go to the graph for that purpose. D only has one outgoing vertex to E, so we expand it so that E is N. And now we have to evaluate, did we just find a shorter path to E? What do you think the answer is going to be? Of course we did. How do we know? Because G of E is infinity, F of E is also infinity. We had never found a path before to the destination. This is the first time we actually touch the destination. So it has to be, quote unquote, a shorter path than the one that, quote unquote, we have found, because we haven't found anything yet. Okay? So what are we going to do in the algorithm? In the algorithm, the condition is going to be true in this case. So this t value is g of whatever c is plus the edge of c, the cost of the edge cn. So translating it back to our graph here, it's going to be 2 plus the g value of d. So when we look at the spreadsheet, the g value of d is 2. 2 plus 2 is 4. And 4 is less than infinity. Is that okay? Because we are comparing 4 to g of n, or g of e in this case, which is infinity. So 4 is less than that, so we have to do a whole bunch of updates here. We have to first add vertex e to the set O. Okay, so we'll go ahead and update O here. So it still has A in it, but E is now added to it. And then we have to update the previous. Okay, so we'll look at the previous here, copy and paste, and then we are just adding this one extra thing. So, oops. The previous of E is D. And then we also have to update, oh, wrong cell to update. Let me change it to here. There we go. We also have to update the F and the G values. So the G value is going to be the same as the F value in this case, because E is our destination. So we have a 4 here, and then we copy and paste here, and this is also going to be a 4. If we go back to the equation, or go back to the code, you can see why they are the same. The way we update G is, okay, we'll just copy T. T is 4, by the way. But when we update the F value, G of n is 4 plus the heuristic value of n to x. But x is E, so we are looking at the heuristic value of from vertex E to vertex E. And that's going to be 0. Okay? So that's why F and G are the same in this case, because n is E and E is my destination. Okay? So that concludes the for each loop, because we only got one outgoing edge in this case. We go back to the outer loop. We ask, is O empty? Well, let's take a look. O is definitely not empty. We ask the second question. Does it look like we might be able to find a shorter path? In other words, we look at the F values and say, is any one of these F value less than the G value of the destination? What we are really asking is any estimated length, is any estimation of a shortest path still shorter than the known shortest path to the destination? That's what we are asking. G of E was just updated to 4. And then when we look at the F values, well, we got a whole bunch that are less than 4. So we can't stop yet. Now, since we cannot stop, we are moving on to the second line, which is finding the one that looks the most promising. So between vertex A and vertex E, we're going to find the one that has the smallest F value. And it's not surprising, between those two, A has a smaller value. So we look at A and go like, well, since F of A is 3.5 and F of E is 4, we choose A to expand this time. So we choose A to expand. That leaves only E in the set O. and then we look at all the outgoing edges from A. So we look at the outgoing edges of A. One goes to D, one goes to C. Well, we'll first take a look at the one to D first, okay? So we take a look at this one and say, okay, what about this? Then we go back to the algorithm, we calculate what is the value of T. The value of T is the G value of A plus the distance between vertex A and vertex D. G of A is 3.5. Okay, so G of A is 0.5. And then we are adding 6 to it. Because the edge from A to D has a cost of 6, has a distance of 6. So it becomes 6.5. So T is 6.5. And we go back to here and we ask, is T less than G of D? Okay. What is G of D? G of D is 2, and 2 is not, 6.5 is not less than 2. So for this particular iteration, the condition is false. Is that okay? I know it's really kind of hard to keep track because we have to look at the graph, look at the trace, and then look at the algorithm, and then have to correlate all three together. Is that okay so far? Okay. So there's nothing to update because the condition is false when variable n is vertex D. But we got a second one because we also go to vertex C. So let's find out what happens when we go to vertex C. When we go to vertex C, what is the value of T? T is G of A, which is 0.5. Okay, let me just double check. G of A is 0.5 plus the distance from A to C, so that makes it 0.6. So the question now is 0.6 less than G of C? What is G of C in the trace? G of C in the trace is 1, and 0.6 is less than 1. So we found a shorter path from the origin to vertex C. Is that okay? Yes? Okay. So because the condition is true, now we have to add C back into the set O. So we have CE in the set O, and we also proceed to update the previous. So we copy and paste, and then change the previous of A, so it's not B anymore. The previous of C is going to be vertex A, because we found a shorter path through A to vertex C. So the previous of C is updated to A. We also have to update the G value. The G value of C is not 1 anymore. Instead, it was 0.6. And then the F values also have to be updated. The F values are pretty easy to update once you know the G value, because it is the G value plus the H value, plus the heuristic value. So we are talking about 0.6 plus H of C E, which is 2.5. 0.6 plus 2.5 is 3.6? No, 4.1. Hmm? 3.1?
You say 0.6?
It's 0.6 plus 2.5. Yep, 3.1. Okay. My math is bad. Arithmetics. There's a difference between math and arithmetics. Yes.
Would you please change the color, whatever you change?
Oh, sure.
Please.
You like that? And that. Oops. Undo. Control B. And then here we have C added to the set. Control B. There we go. Would that work? Mm-hmm. All right. So we are now done with the for each loop. We're now back to the outer loop. The outer loop is going to look at the condition, this condition here. O is non-empty. We got that. Now we have to ask, is there anything that looks promising, anything that can potentially beat the shortest path that we have found so far? And then we look at all the values that we have collected. G of E is still the same, so G of E is 4. And then we look at all of these values, go like, well, there's a whole bunch that can potentially be better. So now we expand, we pick up one of these two to expand. There are only two that we can choose from. We can only choose vertex C or vertex E next. And we have to select based on the F value. F of C is 3.1, F of E is 4. Which one should we pick? Which one looks more promising? C, okay? So we choose C to expand it. So once we choose C here, we have to remove it from the set. So the set is now just E, and then we have to look at all the outgoing edges from vertex C. Look at the graph here. Vertex C goes to vertex D, and that's the only outgoing edge, okay? So we say, okay, let's go back and look at the edge from C to D. And what is the value of T? What is G of C first? G of C is 0.6, and then 0.6 plus the edge going to D is 1.6. So the value of T is 1.6. The question is 1.6 less than the G value of vertex D? The G value of vertex D is 2. 1.6 is less than 2 is true. So now we have a whole bunch of updates to perform. So now we add D back into the set. I was trying to do the boldface at the same time. Probably hit the wrong key. Okay, we have to update the previous so that the previous of D is, oh, it's still C. Okay. Okay. I have to unboldface the other one. And then we have to update the G value first. Okay, so we can here unboldface this one because this one is not the one being updated right now. So G of D is now 1.6. And this one is now boldface because that's the new value. And then we have to compute what is 1.6 plus the H value from D to E. So the H value from D to E is 1. So it's 1.6 plus 1, which is 2.6. So copy and paste. The F value of D is no longer 3. Instead, it is 2.6. Boldface. And then change this one to non-boldface. There we go. Is that good so far? Okay. So now we're done with the inner loop, going back to the outer loop. Going back to the outer loop is asking, is O empty? Nope, O is not empty. Is there anything that looks promising? Anything that can potentially beat the shortest path that we have found so far? And when we look at this and go like, yeah, we still got a whole bunch of stuff that can definitely beat it. So now we choose one of these two. Out of D and E, we choose one. Whichever one that has the lower F value is the one that we choose. So between D and E, the one that has the smaller value is D. So we choose D here. And the only outgoing edge from D is going to vertex E. So we first compute what is the T value. So we go back to the algorithm. The t value is the g value of vertex d plus the edge going to e. The g value going to d is 1.6, and then from the graph we can see the distance of this edge is 2. 1.6 plus 2 is 3.6. Okay, so we go back to the algorithm and we go like, yep, okay, so is 3.6 less than the g value of e? And the answer is yes, okay, because the current g value of e is 4, t is only 3.6, it is less than. So now we have some updates to do. We are officially adding e back into the set O, but it doesn't really change it because it's already there. And then we have to update the previous stuff, which is not going to be visible because it is already coming from the vertex D. So even though we are quote-unquote changing it, it is not visible because it's already there. But I'm going to boldface it anyway. And then we look at G, the G values. And this time we are updating the G value of E, so it is now 3.6, which by the way is the length of the shortest path already. But we wouldn't know at this point. Okay, so we unboldface this, and we update this as well. The F value and the G value are the same because this is our destination already. All right. So at first glance, we have found our solution, okay? But the algorithm doesn't think so. Because when we get back to the algorithm, it will ask, is the set empty? Nope, the set is not empty. It's one vertex left. And then the second question is, does it look like something is promising here? So when you look at all the F values, yeah, there's a whole bunch that are less than the current F value to the current G value to the destination. So it will proceed to choose the only vertex left in the set, which by the way is vertex E. But that's okay because vertex E has no outgoing edges anymore. So there's nothing to explore. But at the same time, we have to take it out from the set. So the next time we go back to the beginning of the outer loop, O is now empty. And we're done. Is that okay? So we found the shortest path, but not from the first time we touch the vertex E. The first time we touched the vertex E, that wasn't the shortest path. But we found a shorter path later on, and then we repropagated the values through the second time so that the shortest path, or the length of the shortest path to the destination was updated correctly. Is that okay? Yep.
So basically, the entire algorithm repeats itself twice. First, like prediction for the shortest path, and then just confirm.
Not exactly. The reason why we had to go twice with this particular case had to do with the way I picked my H values. The H values that I picked were not monotonic, in the sense that, I'll show you. Okay, so look at the H values, the heuristic values. Look at the H value of BE versus CD. From B to E, the heuristic value is actually less than the value from C to E. So it is not monotonic. And this is what tricked the algorithm into thinking about, oh, okay, I'm going to explore that. That turned out not to be the shortest path. But the algorithm, because of the way it's structured, it understands that even though I have found a path to the destination, it knows that it may not be the shortest path. So it kept going until the requirement was satisfied, or I should say the condition of the loop is false, then it got out. But that's the guarantee of there cannot be a shorter path anymore.
So the heuristic is critical here to
Yes,
confirm the efficiency.
correct. you can pick a heuristic. Okay, you can hand pick heuristic values to make A star perform worse than Dijkstra's algorithm. But in general, if you pick the correct and monotonic H values, it is typically better than Dijkstra's algorithm because it's informed. But you can selectively pick certain values for your heuristic function so that the A star algorithm would be less efficient compared to Dijkstra's algorithm. You can trick it. Yep.
So the heuristic, you thought it was being used in order to say these paths are the shortest, these paths cannot be, so we do not even explore, right?
Correct.
In that case, if you started to not use the heuristic to figure out when to stop and just explore every path,
Mm-hmm.
then it would just be the first search.
It will be a breadth first search. Yeah. So in the case of breadth first search, it's a truly uninformed greedy algorithm. You just pick whatever seems to be the most promising, but you're not predicting anything. The predicting part of the A star algorithm is its strength, but it's also its weakness. Because if your heuristic function is not monotonic, then it can be led to go to explore a portion of the path that cannot possibly have the shortest path. But in the end, it will still find the shortest path. It's just that it might take a detour before finding the shortest path. Yep, go ahead.
Could you have H
Metric. It depends on the problem, so it's not always possible. So the way you look at a graph representation is it is not always representing points in space. Sometimes these can be states of a processor, like what values are in each register and so on and so forth, and you're trying to compute a particular value. And then the edges they represent instructions. So you can go from this state of the processor to this state of the processor by going through this instruction. So now you're trying to find the shortest path of this original state of the processor to the desired end state of the processor. But what is the shortest sequence of instructions to go through to go from the start state to the finish state? That becomes the problem, right? Because you can use a longer sequence of instructions, or you can use a shorter sequence of instructions. So in that case, the estimate becomes, okay, how do you estimate? How do you estimate the distance between a certain state of the processor to the end state of the processor? You can count by how many registers are different, okay, for instance. That's easy to compute, right? You can look into, well, that's probably the easiest one, because most instructions can only change one register at a time. So if there are 5 registers that are different, you're almost guaranteed that there are 5 instructions in between. Is that kind of making any sense? Okay. I'm using an example that requires some knowledge of cisp 310, so it may not be the best example I can use. Yes. Any other questions? Yep.
Is it possible to validate the heuristic to see if it's monotonic or not? If it's not, then just to see or predict either we can use a star algorithm or just go to a algorithm?
Okay, that's a good question. The question is there a way to check whether a heuristic function is monotonic or not? The answer is yes, but in order to analyze whether a heuristic function is monotonic or not, you have to analyze the graph. In other words, in this case, the reason why this heuristic function is not monotonic is because h of CE is more than h of BE. But until you analyze the graph, you wouldn't know that the path B cannot get to E without going through C, but it can actually go through AD also. So until you actually analyze the graph, you cannot tell whether the heuristic function is monotonic or not. So that becomes kind of the tricky thing, because by analyzing the heuristic function, the amount of time to analyze the heuristic function is probably the same as going through the A-star algorithm itself, so it's not going to buy you anything. In general. So in general, the best way is to use domain knowledge of what the graphs are representing, or what each vertex is representing, and then find a heuristic function that is guaranteed to be monotonic. Such as in the case of a map, the over-the-air distance between 2 points is guaranteed to be monotonic. Any other questions? Yep.
You have the heuristic dynamically update itself as we're going through the graph. So if we start at being 1 over e, somewhere in the middle, can we say that the heuristic for the point we're sitting at is going to be the shortest path we can?
Okay, so we did not update the heuristic function as we go through the algorithm. Okay, so the question is, can we update the heuristic functions during the algorithm and still guarantee to find the shortest path?
As we go through the graph, we assign the heuristic value to each node based on as we take and so forth. So we
Can you
build our
refine
heuristic-
it? Can you improve the accuracy of the heuristic function as you go through the vertices? Now the heuristic functions are an estimate from a vertex to the end vertex. So in order to improve the accuracy, you have to go through the vertices between a vertex and the end vertex. So I'm going to guess the answer is no. You cannot actively, not in general. Okay, maybe in certain problems you can, but in general, I do not think you can. But that brings up a new question. The new question is, if I can guarantee, okay, that I can dynamically update the heuristic function, but that heuristic function is still guaranteed to be an underestimate, okay, or not overestimated, would the A-star algorithm still guarantee to find the shortest path? Okay, do you guys understand what the question is? So the heuristic function are no longer statically defined. Every time you call BE, okay, h of BE, it can return a different value. But it's guaranteed not to overestimate, okay? So the question is, given that kind of heuristic function that can be updated dynamically, but still guaranteed not to overestimate, would the A-star algorithm still guarantee to get its job done? And the answer is yes, okay? Which is really cool because, you know, if you think about routing in networking, the estimated number of hops between two particular routers can change over time. Okay, and that's the whole idea of, you know, how routers work, is they can gradually find a shorter path between the routers. So the A-star algorithm will still work in that case, as long as the H values are guaranteed not to overestimate. The ideal case is the H values are the same as the actual length of the shortest path between the vertices. That will make it fully informed, which also means, you know, you will have to explore the least amount of vertices and edges to find the shortest path. Questions? Yep.
Can you track if heuristic function is overestimated or underestimated, or is still underestimated?
Yeah. Okay, so I'm gonna restate the question. If we have a heuristic value that is overestimating, how do we know it is overestimated? Would that be a good way to rephrase the question? Okay. And the answer to that is you wouldn't know until you analyze the graph. You wouldn't know until you analyze the graph, because if I give you an overestimate here, okay, without showing you the actual graph or without showing you the values of the edges, you wouldn't be able to tell just by eyeballing it. So to identify your H value is overestimating means you have to find the shortest path first, and then you compare the length of the shortest path to the H value, and then you double check and make sure your H value is not more than the actual length of the shortest path. So no free lunch here. Not even brunch. Any other questions? Those are all very good questions.
So basically, in case that it cannot basically be saved from overstating or
Overestimating.
right? So basically, it's a negative part of the A-star algorithm.
So with the A-star algorithm, the real key to make it successful, to make it useful, is to find a heuristic function that is guaranteed not to overestimate, easy to compute, and yet it is informative. That becomes the biggest trick of the A-star algorithm. And I cannot tell you how to find your heuristic function because it depends on the nature of the problem. So if each vertex is representing a point in space, then you can just use the straight line between two coordinates as the underestimate. And that's a really, really useful underestimate. It works really well. But if the points or if the vertices are representing states of a processor core, then depending on what you're supposed to do, you can count the number of registers that have different values between a particular state and the end state. That may be a usable heuristic, maybe not. It depends on what you're planning to do with it.
Still not one.
No free lunch, yes.
There is pretty much no way to automate the heuristic estimate, right?
You can make the heuristic function learnable. In other words, you cache it. Okay, the more problem you solve, assuming the graph itself doesn't change. Okay, you're only changing from which state to the same end state. Then you can learn, the actual shortest path as you go. So you can start with a heuristic function that is only an estimate, but as you learn the actual shortest path, you cache it, you actually store it. So you're gradually replacing the estimates with the actual shortest path, so your heuristic becomes increasingly accurate in that case. So you can use that approach, but that hinges on you're using the same graph, and you're using the same vertex as the destination vertex.
That looks a bit like a neural network.
Hmm?
It looks a bit like a neural network.
It might look like that because of the vertices, looking like neurons, and then the edges looking like how do you call those synapses, right? The connection between neurons. But these two are not really related. Yeah, neural nets are interesting, because everybody talks about neural nets or deep learning neural nets these days. Yep.
What if you have multiple shortest paths?
Hmm?
What if you have multiple shortest paths?
If you have multiple shortest paths, A-star will find one of them.
How do you know which one?
You don't know because of the choices. Let me go back to the algorithm first. So when you have ties, okay, so given this particular step, when you have ties where multiple vertices have the same f value, depending on which one you pick, okay, that can determine which one of the shortest paths are you going to find. But if they are of the same length, then it really does not matter because you can take any one of those paths and it will still give you the same length.
Dijkstra's would give you all of them,
Dijkstra will only still give you one shortest path. So none of these algorithms will find all shortest paths between two vertices. Which is interesting because over the break on Thanksgiving Day, I was driving from Sacramento to San Francisco. Okay, so you think, okay, how is that possibly related to the A-star algorithm, right? It has everything to do with it, okay? Because when Google gives people alternative paths, like, oh, you might want to consider taking this path, it might save you 6 minutes, right? It's giving the same alternative to every single car along that path. It's not probabilistic. It's not looking at, okay, this path is 2 minutes shorter and that path is 6 minutes shorter. So I'm gonna just throw a dice, okay? I will divert X many cars through this route and I'll divert more cars through the shorter route. Okay? It's not probabilistic. It will send every single car to what it thought was the shortest path at the time. And what is that gonna do? The shortest path now becomes the longer path. because every single car is going that route, right? So, it leads to oscillation because now, as soon as the Google engine, starts to collect the data, they go like, oh, this path is really, really bad. It used to be the shortest one, now it's really bad. It will try to divert all the cars to what seemed to be the shortest path at the time, but it's going to update the suggestion to every single Google navigation map at the same time. So it's going to lead to oscillation, which is also the same kind of problem of automated investment programs, where they look at the trends of different stocks and they all make decisions at exactly the same time, really, really, really fast. That was a question. Go ahead.
And Google is like 15 minutes late? Or 10
I do
minutes
not know
delay?
about the lag.
So basically by the time you think.
Yeah, and that's exactly what I experienced. Because it's trying to divert everybody through a lesser used road, which would otherwise be a shortest path if there's only like a few cars going through that route. But because it's diverting a whole bunch of cars through that smaller route, so it just backed up at the stop sign because it was not designed to handle that much traffic. So what Google should have done is to do it probabilistically. It's like, okay, this is a shorter path, but I'm just going to divert like maybe 45% of the car through this route, and I'll keep 30% of the car in the original route, and then the other going through this route here. Just kind of do it probabilistically instead of sending everybody through the shortest route. Yep.
I believe Apple Maps do that. I believe Apple Maps do that probabilistically choice.
Okay.
Yeah, because whenever you go and there is a road that is filled with a traffic, it becomes red, and the phone and it just gives you, even though that is shorter path and quicker path, it will give you another path.
Well, but that can also, you cannot tell until you have two devices that are actually at exactly the same location, and you see, one is giving you a suggestion going in one direction, and the other one gives you a suggestion going in a different direction. But if it's just one single device, then you can't really tell whether it's probabilistic or whether it updates fast enough to know that, oh, this is not the shortest path anymore. Any other questions? Yep.
For the, let's say there is one short path,
Uh-huh.
you can manipulate which one to find.
Yes, you can. Yep. So the heuristic value, because the heuristic value impacts the f value. The f value is basically the g value plus the heuristic from whatever vertex is that you're considering to the destination. So by altering or by controlling the h values, you can influence which one of the shortest path that the algorithm is going to find. Yep.
Is that true if you have two shortest paths that have all the same vertice values and all the same lengths?
If you have two paths between the two vertices and they have exactly the same
Like all the
cost of edges,
all the edges,
right? So now it depends on the heuristic
So it's
values.
like 0.5.
But what about the heuristic values of the vertices in between? Are they all going to be zeros? Are they all going to be like absolutely dead on, or what? Because the heuristic value is what is steering the algorithm of which one to explore first.
But if they have the same edge like this, it's
Okay, so all right, so let me see if I can show you what's going to happen here. So we'll consider a very kind of special case where you have a start vertex, you have an end vertex, and then you have two alternative paths, and they are symmetric in every way. Okay, is that kind of what you're looking at? And then we are assuming the edges are of exactly the same cost, and then the heuristic value of these two are the same. The heuristic value of these two are the same, okay? So they're entirely symmetric. They're mirror images of each other. Is that okay?
yeah.
All right. So what's going to happen is it's going to leapfrog. It's going to zigzag like that. But it also depends on the heuristic value, because if the heuristic value is exact, it can just latch onto one and just go that in that one single direction. But if the heuristic values are underestimates, then it's guaranteed to leapfrog or alternate between the two. Because if the heuristics are always underestimating, then by the time it gets here, this looks better. This looks better. It explores this one, and then you try to explore this one, and then by the time this is explored, this one will look better, because the heuristic value is smaller. So it's always the other path that looks more attractive. As you start to chew on the grass on this side, the grass on the other side starts to look better, yes. But you have to start chewing on the grass on this side first. Yep. Is that okay? So do you guys want to code this? Turn it into a program? If you were to turn this into a program, which programming language would you choose? Of all the programming language that you can choose, if this becomes a homework assignment, would you code this in C++? Would you code this in Java? I would do it in JavaScript. I would do it in JavaScript because it has map. Map is super useful for something like this. C++ has map as a template class. Yep. Any other questions about the A-star algorithm versus Dijkstra's algorithm? No questions. Okay. So what if I throw a small wrench into this entire thing and say, well, the transitions are probabilistic. Sorry, that's my phone. Okay, so let me tell you what it means when I say the transitions are probabilistic. So let's say you're in a particular vertex. If you take an action, if you decide to do one thing, there's a chance like 60% going here, end up with this vertex, and 40% chance ending up over here. Okay? So you can make a decision of what you want to do, okay, which determines which direction. But that alone does not guarantee you to be here or here. Instead, it is probabilistic. Okay? So how would that affect the process of finding the shortest path? Okay, so first of all, is the problem, do we understand what the problem is? Or how I extended the problem of searching for a path in a graph. Yep.
So you basically don't have cost, you have only probability, right?
You still have cost. You still have cost, except you have no control over, okay, so we can still have a cost of 6 here and we can have a cost of 7 here. Okay? But you have no control over, by performing this action, will I end up in this vertex or will I end up in this vertex? That is completely a throw of the dice. Okay? But you know the probability distribution. 60% of the time you end up here, 40% of the time you end up here, and the cost is also deterministic. Okay? If I go in the top route, it's going to cost me 6 units. If I go through the bottom route, it's going to cost me 7 units. But which way it splits is completely probabilistic. So how would that affect the algorithms that we have mentioned? It won't work. It just won't work anymore because Dijkstra's algorithm nor A-star takes into this kind of consideration. So you have the algorithms won't work anymore. And it's even hard to describe the solution. In other words, how would I describe the length of quote-unquote the shortest path when it is all probabilistic? Yep.
Don't you have to define some type of coefficient that assigns the percentage value?
Yep. You have percentage values, but the expression of the length of the quote-unquote shortest path becomes difficult to express.
Yeah, but I'm thinking that percentage would be worth more if it's more probable in terms of the overall distance.
Well, as it turns out, this generalization is worthy of a dissertation. Turned out to be mine. So we're not going to talk about it today. I was just kind of like, trying to just make a slight generalization of the original search algorithm, problem, just by saying, what if it is not deterministic? Well, as it turns out, a lot of stuff doesn't work anymore. Yep.
Do you have like a real life example of when that would happen?
I like that. Okay. So a real life example where you have probabilistic transitions, right? Okay. Let me turn off the phone ringer first, okay? Because it's okay. Is it off? No, it's off. Okay. So imagine that you are a robot. You're a Roomba, okay, robot, okay, and you're working in an office environment. So have you guys been to like large office environments, like the Intel campus in Folsom? Anything that's large, okay? So let's just say that sometimes you lose track of where you are in the building, or somebody turned you off, okay, bring you to some place still in the same building, and then turn you back on, without telling you where you are, okay? That can potentially happen, right? So now the question is, your battery is running low, you have no idea which floor you're on, you do have a map of the entire building, okay? And you can scan around you and say, okay, I see a wall over there, I see a hallway over here, I see a door over here, and so on. So the question is, how do you find the shortest or the closest charger given that situation? Now, there are many places within a building that can look the same, okay? I see a door on my left-hand side, a hallway in front of me, another hallway to my right-hand side, and a dead end to my back, okay? That can happen at multiple locations within the same building. Is that okay? So they can be like all over the map. The chargers, on the other hand, are at certain locations. So now it becomes a probabilistic kind of thing. Go ahead.
Are the charges guaranteed to be on the wall?
The chargers are on the map, so they're known to be at certain locations. Yes, you can assume they're next to certain
Next to
walls. Certain walls, yeah. So then that problem turned out to be a sub-problem of what I just mentioned, because there's probability involved now. You and then you. Go ahead.
Wouldn't you have to determine like where your battery's at? Because if your battery's really low, then you're gonna take the riskiest route that gets you like the shortest path, but it has like the lowest percentage of probability. Because
Why would you do that?
Because you only have like 1 minute left till your battery dies. Whereas if you were to explore, like I was saying earlier, like the percentage value would have to have some type of conversion value to the overall distance. Because the riskier you want to do it, then the percentage value will worth less.
Okay, let me remember this question first, and you go ahead.
I was gonna ask you, is it
So the first thing you need to do is to scan around you, look in the map, and say, I could be here, 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 could be here. Okay? So those are the possible locations that you can be in. And in my dissertation, I called it a confusion set. Because you're confused, you don't know which one it is, it can be one of these, okay? So now the question is, what is the next state that you can transition to? Okay, if I decide to go down the hallway by one cell, okay, I can help to disambiguate where I am, okay? But I can move it away from a charger potentially. So which one, should I do that or not? Should I try to disambiguate so I know exactly where I am in the building? Or should I try to go for the closest charger, assuming that I'm here and the closest charger is right behind me? So now it all has to do with probability. Because if you have 6 possible locations, then you can be, assuming the distribution is even, you can be at any one of these 6 locations. So 16% or so, okay? 16% of the case I will be here, 16% of the case I'll be here, and so on. But if I'm here, I'll be really far away from a charger. If I'm here, I'm kind of close to a charger, and so on. So it turns out that that problem can be cast into the problem that I just mentioned. No, because it becomes that same problem, which is you take an action, you either turn around and move one cell, or you just move one cell, or you turn around to the back and move one cell. That is an action you can perform. But by performing that action, you end up at a different confusion set. But which confusion set do you end up with is probabilistic, because we don't know exactly what the current location is. It would further refine it it cannot make it worse, it can only refine it. But it does boil down to the same problem of an action can end up at multiple states with known probabilities. Yep, go ahead.
Basically, both of them at the same time, you move toward thinking that it is, but you're also moving to
Ambiguate.
because you go to where a charger is, you don't actually go on a shorter path, you still so.
Well, it turns out to be, there's a weighting factor in it. So let's say there are 4 locations, okay, that look exactly the same as what you're currently in, okay? So out of the 4 locations, potential locations, one has a charger really close to the back. The other 3 do not, okay? So now the other 3 has the potential charger like 3 cells ahead of you. So the question now is, which outweighs which? Okay, is the proximity of the charger behind me outweighs the other 3 possibilities where the charger is 3 cells ahead of me and then make a right turn, or should I just kind of go back and try to find that one first?
Basically, if you do go just the disobey
Mm-hmm.
does it matter which way you go?
You basically do both at the same time. That's basically what the algorithm will end up doing by taking into consideration the chances, the probabilities, and also the distance to the closest charger. So we basically look at all of these factors, weigh in, use the probability as weights to multiply to the closest distance of the charger, and then combine these to determine what they should do next. But it would still be a problem similar to what we are trying to solve with A-star and Dijkstra's algorithm. But those algorithms cannot solve this problem because they can only deal with deterministic problems. Yep.
Does it also apply with like CPU instructions? If the value you're looking for is cache or not, like it's just chances to cache.
Oh, okay, yeah.
Is that accurate to say?
So if you take into the probability of something is being cached, yes, then it becomes a probabilistic kind of thing. But to acquire that probability distribution may not be easy, because you might be dealing with a case where the probability distribution itself is not even known ahead of time. So that becomes an even more difficult problem to solve because it's not a known probability. How many people play backgammon as a game? I don't play it. That turns out to be one of the cases of this kind of thing too. Because I think in backgammon, you have to throw dice. It is not adversarial, you're not playing against somebody, and you want to get to a certain end state as quickly as possible. Is that right? You do?
So basically, it's trying to hit against
Okay.
they're going opposite directions.
Okay, but does what you do influence your opponent?
Yes.
You do? Okay.
Because they can only choose spaces that are either monopoly
Okay. Okay.
pieces they can't.
Okay, how about Mahjong, the single player Mahjong? That would be single player, non-adversarial because you don't have an opponent, and it's probabilistic because you don't know what is under the tiles. So that becomes a problem that the generalization of the A-star versus Dijkstra algorithm can be used to solve. So those problems do exist, and well, I made a dissertation out of it, so I'm kind of thankful. running out of time, so I'm gonna see you guys on Wednesday. And on Wednesday, we'll start to get into the big O notation. Okay, there are no notes yet, so I will make those notes available sometime before Wednesday.
Professor?
Yep.
Can we have dynamically changing